Alright everyone, welcome back to another video on scientific computation using Python. Now in this video we're going to talk about a very interesting concept that is really helpful when you're dealing with expensive function called returns. Okay, and now here I mean when I say expensive I mean functions that take a lot of time to compute, or it takes a lot of memory to compute and all of it. Right, so in these cases what can be done to make these functions faster is what we're going to do today. Alright, so to explain that, as an example, I'm going to take this function, Fibonacci function that we did earlier. So what does it do? It actually calculates the nth term in the Fibonacci sequence. Right, so this is the function that I have over here. So let's understand what it does. It takes the nth value, okay, and it checks if the nth value is an integer. And then if it's an integer, that is greater than 1. Right, if it's not an integer and if it's a negative integer, right, in those cases we don't want to do any calculation. We just want it to go and do calculations and return the term only if it is if it is a positive integer. Right, so what it does is it checks it. If it is valid, if it's a valid positive integer, it'll go and calculate the Fibonacci terms. Otherwise it'll just return 0 with a print statement saying that, hey, you entered an invalid term. As simple as it is. Right, now if you look at the case where it's going to calculate the terms, it's very simple. It checks if n is 1 or 2. If in either case, it calculates, it returns the value 1. Okay, it returns the value 1. Otherwise it'll just it calculates the previous two terms that are there in a recursive call and returns the value to us. Alright, now if I were to check this function, okay, now if I were to run this to calculate up to take say 10 terms, okay, look at it, it just finished almost instantaneously. But if I were to go for 20 terms, okay, will it finish instantaneously? Kind of. We see it's kind of finishing fast. So let's actually time it now. If you were to import to check the times, you can import this function called time. Import this method, library called time. And because this has a function, function called time, which will help us a lot. So I'm going to call a variable called start. I'm going to call it time.time. Okay. Now what this time function in this library time does is it just gives me the time that is elapsed from some reference point in the past till now. Okay, it's going to give me some reference point, say like 1 hour passed, this many seconds passed from some reference point in the past. Okay, and here I'm going to call a new value called end. Okay. So now with these 2 points we can again understand how much time it elapsed for this entire thing to go ahead. Now what we can do is we can actually put a print statement and actually check how much time it took. So for that we can call in the f string and say time elapsed for simple fib function equals we can just say end minus start seconds. Okay, now with this I think we'll have an idea of how much time it actually took for the function call to work. Okay, now if I were to run this for 20 terms, it took about 0.01 seconds. Not bad at all. Now if I were to increase it to 30 and run it, 1.12 seconds. If you notice properly, the computer started lagging. The program started lagging. And here's what I mean. See, you can clearly see up to that 28th term it kind of calculated alright, but for every other term it's taking a lot more time and it's kind of getting slow. And I don't want to test it with a really high value because it will take a lot of time. And look, to calculate up to 30 terms it took 1 point some seconds, but to calculate the next 5 terms it took a lot, and it totally took 11.8 seconds. Now that's terrible, right? Why is that? That is because of this problem. Wait, what did I do? No, I think I didn't copy it properly. That is because we got into this problem. So let's suppose we want to calculate the 40th term in the Fibonacci sequence, right? Okay, now to calculate that, first what we have to do is we have to go and calculate the 39th term in the Fibonacci sequence first, and then we have to calculate the 38th term in the Fibonacci sequence first. Okay, now do we know these values a priori? No, because our function does not save any of these values anywhere. So we have to go and calculate it. So to calculate the 39th term, you have to go and calculate 38th term and 37th term. And to calculate the 38th term over here, you have to go and calculate 37th term and 36th term over here. And look at that. Then the first function call created two function calls. And the second round, you have two function calls creating four function calls. And then in the next level, you'll have 8 more function calls because each of these terms will generate two more function calls each, right? Now, with just like that, with a matter of time, the function calls start increasing rapidly, very rapidly, right? And all this time, if you look at it, if at all we stored any one of these function calls a little a priori, we can just use it directly, right? Isn't it? So that is what memoization does. I'm going to cut this and I'm going to put it on the top so that you guys can, so that everyone can see clearly. There. So this is what we're going to do today. What memoization does is that you just calculate the calculate the value of an expensive function call. You store the result of that expensive function call separately, and then what you do is that when the expensive function call is invoked again, okay, fetch the same data instead of calculating it. As simple as it is. The idea is very simple. So if at all you have certain values you have to calculate, and if that calculated value is already calculated and kept somewhere else, you go and fetch it, right? That's all there is to it, right? Now, how do we invoke? That's all fine. In theory, it's fine. So in practice, how do you go and implement this? How do you go about with it, right? So for that, what I'm going to do is I'm just going to copy this function, right, and paste it here, and I'm going to call it memo. Tell that this is a memoize function. I'm going to call this as a let's say memo fib dictionary. I'm going to create an empty dictionary like this. Why dictionary? To just store the values, right? Now, what this function does right now is just goes and calculates everything, but it does not have any feature to go and save the data, right? So first, what you do at these points, it's going at these points. Let's actually go and save the data first. So it has to return 1. So here, the memo fib, the dictionary with the nth key should be equal to 1, right? Now what I can do is I can just write memo fib of n, and that will do. What it does is it just goes and calculates, just goes and finds the value of n, saves that particular n value of n with the key n in the dictionary over here, this empty dictionary. So it populates it and then returns the particular value. That's all there is to it, right? And now what we can do is that we can do the same thing over here. First, we'll just go and calculate this value and save it in our particular location like this. And what is that? The Fibonacci function recursively being called. And now, note, we are not going to use this because this function has no feature to go and save it. But this function has the facility to go and save it. So we have to call fib memo. And here also I'm going to call fib memo, right? Once I go and save these, right? Once I go and fetch this function recursively inside it, I just have to go and calculate this value, and I return this particular value. Now here's my question. Here's my thing. Okay, if the particular value is not present, it goes and creates those values and saves it, right? And return the particular value. All fine. Now, what about values that are already calculated? There could be some values that could be calculated, right? Like for instance, if I were to calculate Fibonacci of 5, let's say it needs to calculate Fibonacci 4 and Fibonacci 3. But definitely, if I were to come up to Fibonacci 5, I would have calculated 4 and 3 earlier, right? So what do we do for that? That is where we are going to do a little bit of a master trick here. We're going to say if n is what was it? Let me think for a second. If we had to check if n in memofib, if that key index, okay, for the particular value of n is already there in the memofib, then we don't have to do all the calculation. We can just fetch that particular value and return it. So I'm just going to call return memofib of n. That's about it. As simple as it is. You just go and fetch that particular value and send it to return it, and you don't have to do all those calculations. But if that particular value is absent or not present, right, then we'll do the else state. When we do all the calculation, save it and then return it. As simple as it is, right? Now let's actually check how much time does this take. So we have our n, which is 35, which is 35. Now let's actually call the same thing. We'll put it in side by side for comparison. Alright, and I'm going to call this as start 1, and I'm going to call this end 1, okay, so that I have different timestamps for this. So I'm going to copy this and paste it over here. Alright, and instead of calling it sample, we can just call it modified fib function. The time elapsed for the modified fib function will be end 1 minus start 1, right? So we got this. Now, is there any issues? No issues so far. There are just some there are some issues, minor issues, like keep the code a little tidying up. Is that it? Yeah, I know. These are just like like sanity checks. I mean, these are like absolutely not needed. This is just to make the code look a little prettier. That's it. Now, if I were to run this code, check this out. It takes it's taking about 7 seconds or 8 seconds now to finish. Okay. If you look at it, my mistake. I forgot to make an addition here. I'm just calling the same function twice. Idiot. That's an idiot thing of me. Anyway, now if you look at it, if you look at it, on 2 runs, it each they calculate 35 terms. It took 12 point some seconds. Right. Now I'm just going to call fib memo instead of fib. Okay, and I'm just going to call it again. So the first function, we know it is going to take around 12 point some seconds to do all the calculation. Now we are actually introducing the second function. Let's see how much time it takes for the second one. When you look at that, it was almost instantaneous. The first one took about 13.5 seconds to calculate 35 terms, whereas the second function, the one we did, the modified one, you can clearly see it here, takes less than a fraction of a second to calculate, all because we say the intermediate values in between. Neat, right? Now what I'm going to do is, let me push this. Clearly we know this is not good. This will take a lot of time, so I'm going to comment this out. Okay, now let's actually push this function to its limits. So let's actually calculate the 100 terms and see how much time it takes for 100 terms. Still less than a fraction of a second. That's brilliant. Now let me go and push it to say 10,000 terms. Hey, you might think this I'm like going overboard, and you're right, I'm going overboard. But let's see. It calculated like 10,000 Fibonacci terms up to in 0.33 seconds. Not bad at all. So if I were to push up to 50,000, right, just to get some kick. Now the program is actually struggling even with the memoization and all. But it's alright. Because of the memoization, it's actually able to do all of this better. Now, just for the kick of it, if we just uncomment this part and run our function, I think it will take a lot more time. But hey, if you want to do it for the kick of it, go ahead and do it. But I would suggest not to, because your system might overload. And when you look at that, it took 29.35 seconds to calculate 50,000 Fibonacci terms, right? With that, a memoized function does it, right? Right? So that's how it is. Now the good side of this little tweak is that our function is a lot more better and it's robust and it's able to do all of this perfectly. Now, the downside of this is that our function is a lot more messy and it's not easy to read through, right? Now, if you're good with your code, it's all right. You can easily figure this out. But if you're like someone who's learning this code and you want to keep the elegance of this function over here, what are you going to do about it? What can be done about it, right? Is there a way to simplify this? Yes, there is. That's why the function tools option that is available in Python is going to be really helpful. So in the Python that you have installed, by default you have a library called functools, which is the short form for function tools. In that you pick up this key thing called as LRU cache, and LRU cache means least recently used cache. So what does it mean? It means that hey, if you calculated a certain values from a function recently, it's not going to delete it. When the function call is lost over, that value will be deleted, right? But this function, this little key function, makes sure that that particular value is not deleted. So we're just going to go and stack them up, and to wrap it around a function, you just put an at in just front of the function and call LRU cache like this. So what does this do is that this function now will go and keep track of all the values that this function is going to return, right? And it's not going to clear them up. It's just going to store the last few values of this function in its memory, in the memory. That's all there is, so that we can go and fetch it, right? And and you might wonder, hey, how many terms should it go and save? That could be a question, right? So that's where it has this feature. It's called max size. Now by default it will go and save last 128 entries, but if I were to put say 5,000 entries, let's say, it can save up to the last 1,000 entries. So for our code right now, let's actually test our code with 100 entries, right? All I did is I'm just going to put this LRU cache with a maximum size of 1,000 entries. So I'm just telling it to say 1,000 entries like this, right? Now I can actually go and uncomment this part and uncomment this part, right? And run. Let's see how this works. And how about that? Now our function, with just a little bit of help from our LRU cache, okay, the least recently used cache, is able to calculate 100 terms of Fibonacci sequence in 0.00048 seconds, and that's brilliant. Other memoized function is able to do that just the same range of time. Now we're up for something. Now if I were to go and increase this to 10,000 seconds, let's see what this is up to. Now how about that? Both of them took about the same order, 0.3 to 0.31. They're coming neck and neck, right? Now if I were to push it to the same 50,000 seconds, right? So say 50,000 terms. Now both of them will take a lot of time, right? Both of them will take a lot of time, and let's see how this turns out to be. Let's check it out. Come on, 43,000, 44, 45, 46, 47, 48, 49, 50, and then we went into the memoization function, and it's 28, 29, 30, 31, 32, 38, come on, 40, 42, 43, 44, 45, 46, 47, 48, 49, and 50. Yeah, look at that. Our function took about 30 seconds to calculate, whereas the memoized function took about 28.9 seconds to calculate. Now how ridiculous is that, right? Not bad at all. It's like it's actually doing a lot more optimizations over here. Now, just for the kick of it, if I were to save 50,000 values and run this again, I think this will be a lot more faster. Watch. Because why 50,000? Because I'm going to tell I have to store up to 50,000 values. So it's still within the cache limit of this function, right? Boy, that's a lot of calculations if you agree with me. Right. Now that function, now the first function is over, the LRU cache function Fibonacci sequence is over, whereas we're doing the Fibonacci sequence function with the memoization, manually implemented memoization. And let's see, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, then 50. Huh. Would you look at that? It took 30 seconds for the first function to finish, the LRE cache finish, and then the memoization took about 32 point some seconds to finish. Not bad at all if you ask me. They are the same, both these functions are in the same order of their execution times, and they're working just fine. And if you were to do this without this LRE cache, I think this function will not have any chance of standing next to this function in terms of scalability and the execution time. Right, now there you have it. Now you guys know two methods to do memoization. One is by one inbuilt tool called LRU cache that is available in the function tools module of Python, and other by a manual implementation just by using a data structure memoization, just a dictionary. Right, now why do I talk to you guys two methods is because one to take the advantage of an already existing method in Python, right, so that you can use it nicely. And I also taught you guys the manual method because in case if you guys do not know how to go and do it, or maybe that functionality is not available for you in certain cases, you should know how to make it on your own, right? So there you go. You have a manual method in case you don't know how if the functionality is missing, and you have a simple method that is already implemented and to make your job a lot more easier if that functionality is there. And there you have it. And with that, you can make your recursive functions work a lot better. Now that's all I have for you all in this video. Thank you guys for watching, and I'll see you all next time.